Hey, AP Stat students, Mr. Mitchell here. Today, we're going to looking at describing location in a distribution. So for textbook purposes, this would be section 1 in chapter 2. So we've been talking about describing data for a couple weeks now, and we're going to continue with that. We're going to learn some new concepts, but that's really the major overall concept that we're looking at. So let me share my screen. And we're going to go ahead and get started. So we're describing location. So these are 25 students in Mr. Pryor's statistics class on their first test. So here's the data in which they got, all the students. So they want to see how Jenny did. How did she perform on the test? So an 86, okay, it's a B. Is that good or is that bad? I don't know. It's relative to her classmates. Maybe 86 is really good. Maybe 86 is not so good. A B could sometimes be a really good grade or not so good, or maybe it's average in terms of everybody else. So we're going to take this data and we could make different graphs with it, but let's make a stem and leaf. We've talked about stem and leaf before. Here's your stem and leaf plot. We split the stems. So you have there'd be two 60s if there were anything in the lower 60s, but there's two 70s, two 80s, and then there's no high 90s here. So is 86 good or bad? That's kind of what we're trying to look at. So if we look at the shape, we've talked about socks before. So looks like if I turn my head or if I were to rotate the screen, looks like it's roughly symmetric. Doesn't look like there's any outliers. Jenny did better than all but 3 of her students. I mean, that's pretty good. Okay. So one way to describe how Jenny did is in a percentile. Percentile as a distribution is the value with P% of observations less than that. So Jenny scored her 4th from the top of the class. So 21 of the 25 observations are below her score. So really, it's everybody that you're better than. That's the way you want to think about a percentile. You count everybody that you're better than. If you're not better than them, you don't count. So if you tie, that doesn't count. So it's who you're better than. So sorry about that. We would take 21 divided by 25 and we get 0.84, and then move the decimal point twice. That's 84%. So she's in the 84th percentile. All right. And so we could do that for other numbers as well. If we go back to our graph, we can find what percentile different numbers would be. 72, there's only one number better than that. Or, I'm sorry, less than that, I should say. So 72 is only better than one other number. So we do 1 divided by 25. So that's the 4th percentile. Okay. So that's how we would go back, and we could do some other examples, but that's how you find percentiles. It's what percent are you better than? If you're in the 50th percentile, that means 50% you're better than. That also means that 50% are better than you or the same. That's not quite the same. So we talk about cumulative relative frequency graphs. We talked about some frequency graphs before. So these are the ages of the presidents. Most presidents, and again, this is from several years ago. I don't know that our last 2 presidents may be on here. If we expand this to include relative frequency, and we can expand it to include cumulative frequency. So relative frequency is you're going to take 2 and divide by 44, 7 divided by 44, 13 divided by 44, and you're going to do that for all of them. So here's your relative frequency. Cumulative frequency is each time you're going to add it up as you go. So you're going to, the first class is just 2. It's still the same. But then in the next class, you're going to take the 7 and the 2, and you're going to add them together to get 9. And then in the next class, you're going to take the 2, the 9, and the 13, and you're going to add them together to get 22. And so cumulative frequency, when you get to the last class, that's at 100%. You add as you go. Sometimes a cumulative frequency graph could be something that we could look at. clicked the wrong way. So this is the cumulative frequency graph, cumulative relative frequency graph. So you can see it's going up over time. And what you're looking for, one of the things is where's the fastest growth in terms of slope? That's right here in the middle, right there at this bar. That's where most of the presidents were. And you can see it kind of flattening out there at the end. So was Barack Obama, who was inaugurated at age 47, unusually young. So here's 47. The answer to that would be yes. He was unusually young for presidents. Estimate and interpret the 65th percentile of the distribution. So here we come up to, again, the left side is in percents. That's the percentile. So you come, that's about 65. Come over to your graph and then come down. So what's that? About 57, 57 and a half. Okay. So you can see we can read a cumulative frequency graph to find if something's unusual or if something's typical. We can also estimate what percentiles things are. Next, we're going to talk about z-scores. It's all about position. Like, is it good or bad? Is 9 pizzas a lot? If I'm eating that by myself, 9 pizzas is a lot of pizza. If I'm feeding 50 people, 9 pizzas isn't very much. So it's all relative to what you're talking about. So we want to figure out whether something's good, bad, or in between, or big, small, or in between. So one of the things we do is a z-score. Okay. So Jenny scores above average, but by how much? Okay, she's in the 86th percentile, but how much is she above average? So we calculate the mean and the standard deviation. We can use our calculator again to do that, or we can do some kind of Staplet online to calculate that. So we found the mean is 80 and the standard deviation is 6.07. So then our z-score formula, our standardized score formula, so you can call it a standardized score, you can call it a z-score, it's the same thing. So you're going to take your raw score, which is x, you're going to subtract the mean, and then you divide by the standard deviation. That's called a z-score or a standardized score. One thing to keep in mind, the z-score is the number of standard deviations above or below the mean. It tells you how far above or below the mean you are when you standardize things. A z-score is really good for also comparing things that you normally can't compare. So comparing your ACT and your SAT score, they're on completely different scales. 1600 is what the SAT's out of. And I think the ACT's out of 36. Well, how do you compare a score out of 36 and a score out of 1600? Well, you have to standardize them and then you compare them. You can't compare apples and oranges unless you standardize them. That's kind of the idea there. How do I compare an apple and an orange? They're not the same. What you have to do is find the mean of the apples and the standard deviation and find the mean of the oranges and standard deviation to find out if you have a rare orange or a rare apple growing on, like on your property. Like maybe you grow oranges better or apples, you could do something like that. But you can't compare them just, oh, the apples are bigger or smaller than the oranges. Well, maybe they're still big apples, or maybe they're still big oranges for what you have. Again, I don't know that you necessarily grow apples and oranges at the same place, but it's just an example. So here's how we calculate our z-score. So we want to find Jenny. How good is Jenny's score? So we take 86, that was her raw score. We're going to subtract the mean, and then we divide by our standard deviation. So we got 0.99. Jenny's test score is 0.99 standard deviations above the mean. All right, so notice it's a positive number. If you get a negative z-score, you will be below the mean. So that's all the positive and negative, just tells you a direction. You're positive, you're above the mean. You're negative, you're below the mean. And when we describe things on free response type questions, we would want to be more specific. Are you above, or are you below the mean? We don't just say we're from the mean, because that could be either direction. If I am on an interstate from a specific town and I just say, well, I'm 10 miles away, well, that doesn't really tell me, are you 10 miles north or south? Or are you 10 miles east or west if the interstate's running east and west? So we could calculate Katie's score. So our mean is 80 and our standard deviation is 6.07. So let's pull up our calculator here. We're going to take 93 minus 80. Then we're going to divide by 6.07. And we get 2.14. So your 2.14 standard deviations above the mean. Now notice what I did there. I did the subtraction first. You cannot type it in like this. This would be incorrect, and I'll show you. You're not getting the same answer. I mean, think about it. If you subtract these two numbers and you get 13, then you divide that by 6, you're not going to get 79. So if you want to type it all in at once, you just have to use parentheses around the top. Like if you don't want to do two different calculations per se, just put parentheses around the top and do it that way. Or just do the subtraction and then do the division separately. So either way is fine, but you definitely have to put parentheses. Can't do this. This is a no-no right there. Okay. So that is that. All right. We can calculate Norman's z-score. So 72. So to make life easier, if you do second enter, all you have to do is go change the raw score because the mean and standard deviation didn't change. So there's Norman's score. He is below the mean, negative 1.32 standard deviations below the mean. Normally you round z-scores to 2 places. And when we get to section 2, you'll see why we round that to 2 places. All right, so there's your z-score calculations. All right. Let's see. On which test did Jenny perform better relative to the class? So the day after receiving her stats test, Jenny earned 82 on Mr. Goldstone's chemistry test. At first, she was disappointed that Mr. Goldstone told the class the distribution scores were fairly symmetric with a mean of 76 and a standard deviation of 4. So again, she got a lower score on this chemistry test, but did she do better or did she do worse? So let's go to the calculator. So she got an 82. And the mean score was 76. And then what was our standard deviation? 4. So Jenny got a 1.5 as her z-score. When we looked at the other calculation, she got a 0.99. So I know in the grade book, and sometimes that's all students care about is what's in the grade book. In the grade book, the stats test is better. Like an 86 is definitely better than an 82. But in terms of how everybody else did, the chemistry test was harder. So she actually did better on chemistry than she did on stats, if you're going to compare things on the same level. So chemistry test was harder and she did better on that. Let's keep going. A couple more things we need to talk about. All right. So again, describing things in location. What effect do transformations of addition and subtraction, multiplication, and division have on shape, center, and spread of a quantitative distribution? So here's a group of data about Australian students. So here's their data and their guesses about how wide the classroom is. Okay. So really, another good example would be salary. Another example we could look at is if we give everybody a flat raise of $5, or if we take money away from them, we're going to take $5 away from every employee. What is that going to do to the center, shape, spread, our socks concept? Okay. Or if we give everybody a 2% raise, what does that do for the shape, center, and spread? So that's really what we're looking at in terms of maybe this doesn't quite make a connection, but think about it in terms of a job and making money. If they give you everybody the same, like just a raise of $1, what does that do? Okay. So that's what we're looking at. So if we look at the distribution, just the regular distribution, looks like it's skewed to the right. Looks like it's got a peak around 15. It looks like that's right about where the center is too. So shape, it's skewed to the right. It's bimodal. It does have 2 peaks. Center, median guess is about 15. The mean was about 16. If you do all the calculations, there's definitely some skewness, so the mean's going to get pulled that way. Spread, we would want to find our IQR and to check and see if there's any outliers. And there are 4 outliers. So again, I'm not going to go through the whole entire process of finding those. We did that last unit, but we went through it. So these 4 numbers here are outliers. Okay. So that's socks. Went through and did socks. So now what would happen if we add or subtract a constant? The actual width of the room was 13 meters. How close were students' guesses? The minimum guess of 8 meters was too low by 5 meters. The maximum guess of 40 was too low by 27 meters. We examine the distribution of students guessing errors by defining a new variable as follows. The error equals guess minus 13. So you're going to subtract 13 from each observation. What do you think is going to happen? If you just take everybody and subtract 13 from it, all that does is take the graph and shift it. It's going to shift it left. Okay, it's going to take everybody and shift you left. Doesn't change the shape. So when I look at this, look at the shape now. The shape is still skewed right. That's definitely going to change. Okay. Where does it look like the peak is now? The peak looks like it's we're right about 2. Yeah, it looks like it's a 2. Where was the peak before? The 15. That's a difference of 13. So when you shift everything one way or the other, shape doesn't change. Let's look at, just look at range. We could do standard deviation, IQR, and everything, but let's look at the range. You go from 8 to 40. So that's a difference of 32. Here we're down in the negative. So we go from, what's that look like? About 27. What's that? 2, 4. That's a negative 5. So what's negative 5 to 27? That's 32. So the spread, it didn't spread anymore, get closer or spread apart. All it did was shift. Now, what is going to change, the mean, the middle point is no longer in the same spot, but it's going to shift by 13. Okay. So that's really what happened. So here's the overall, here's what happens. Adding the same positive number or subtracting, in this case, we subtracted from each observation, adds to the center, the mean, median, quartiles, and percentiles. So the center is going to change, and your things that are contributing to spread maybe change, but the spread doesn't change at all. Your quartiles stay the same, your percentiles, mean, median, but your interquartile range doesn't change. Your range doesn't change. Your standard deviation doesn't change. None of that stuff changes. So really, the only thing that changes is your center. Spread doesn't change. Shape doesn't change. Okay. So what happens if you multiply everything? So we're going to convert units, or in my example of doing this with salary, instead of giving everybody a $5 raise, we're going to give them a 5% raise. So what does that do? So we got to change our units. So to change meters into feet, you got to take meters times feet, which is 3.28. So that gives you, so we got to change those. When we do that, look what happens. So we're going to give everybody a raise. We're going to multiply. We're going to go from meters to feet. Feet are smaller than meters. So in 1 meter, you're going to have more feet. You're going to have 3.28. So look what happened. Here's the original. Here's the new one. It dispersed. It got more spread. So you can see, you can make the comparison. Look at the mean. The mean definitely changed. Standard deviation changed. The median changed. The IQR changed. The range changed. Pretty much everything changes. But by how much did it change? Well, look at your numbers. How much did they change by? 3.28. Take your calculator. 9.91 divided by 3.02. 3.28. So that's what's going to happen. So let's try to sum this up here. Multiplying or dividing, because dividing is the same thing as multiplying by a fraction. So multiples, the measures of center and location, mean, median, quartiles, and percentiles, are going to change by that multiplier of B. In this case, it was 3.28. That's what we multiplied by. Measures of spread, range, IQR, and standard deviation multiplied by B, but it does not change the shape of the graph. Again, go back and look at your picture. The shape is still skewed to the right. So shape never changes when you multiply, divide, add, or subtract. So that is a concept that we do need to know. Okay. Last thing I believe is connecting transformations and z-scores. Let's think about what is this z-score? Well, you're taking a number, a raw score, and you're subtracting something from it. Well, we just looked at subtracting the error in that problem. And then you're also dividing. Well, I know we multiplied by 3.28, but multiplication, division, potato, if you turn the number into a fraction or reciprocate it. So that's all z-score is. It's a transformation of the data. You're turning it into something else by subtracting the mean and dividing by the standard deviation. So we could take these, here's the test scores, and we could do standardized scores for them. So this was going back to the Jenny and the test scores. We could take all of the scores and convert them to z-scores. And so then you can see, okay, how far is an 85 or an 86? Like, how far is that score? Is it good or bad? How far is it from there? You could see all the scores and see how they relate to each other. And so sometimes we want to standardize things to know, is 9 pizzas a lot or is 9 pizzas a little? Is an 86 on the test good or is an 86 on the test just okay? Again, it depends on what else is going on. It's relative to other things. Okay. And that's it. So let me know if you have any questions. And see you later.